Have you ever wondered how a rendering engine works, such as the one that powers Unreal Engine 5? So, here's my adventure on writing my own renderer, and to make this more interesting, I also add some sort of geometry system. The system in question here is Nanite, so my initial starting point to all of this is to learn some 3D graphics, which is important, for a renderer. And I know that there are a few graphics API out there, such as OpenGL or Vulkan or DirectX. Just like everybody else, I also start with OpenGL, and once I got my first triangle on my screen, then it's time to write a loader to get external model into the engine. Once that is in, the next step is to look into the actual Nanite system. There is a deep dive presentation on Nanite on YouTube, which goes over the actual Nanite system. But the only problem here is it was easy to follow at the beginning, and minutes into the video itself, it started to be too complicated to understand. So then I quit the video and went to the drawing board to sketch out how the whole system would work. If we take a look within the engine itself, we can see that there are colored clusters, and each cluster is a simplified version of the previous cluster. And the magic trick behind this is we switch out these clusters depending on various variables, such as screen space error or distance. With a rough outline and with my basic knowledge on 3D graphics, I went out and coded the engine. First, I started with creating these small clusters. For that, we create a bounding volume around the model, and then we cubify it. And the clustering starts with subdividing that bounding volume, and here we do the actual clustering. This is what I got as the first result to clustering. There are some issues with intersection validation between clusters, where the triangles did not get included within each cluster. Well, fixing that issue reveals another issue. If we take a look at the bottom cluster, that cluster has two children. To fix this issue, we do a connectivity check with a DFS or a BFS to check whether each primitive is connected together. If we stay on the same picture, we can spot another issue where a cluster only has a few primitives. This is more or less straightforward to fix by merging them into neighboring clusters. After all of that and many more fixing, this will be the start of our LOD creation, which will be my next step to this engine. In this step is where we create our lowered resolution of clusters. There are a few methods here that we can use for simplification. The method that I use here is called quadratic error matrix. Is one of the widely used methods to simplify a mesh. For this, I pick out a cluster to test the algorithm or the simplification, and this is what we get at around a 66% reduction. Now, if we plug that cluster back into the model, we can see that there is a gap or a crack between the cluster. To fix this issue, we have to exclude the border edges from being included within the simplification process. After solving many more issues, this is what I get for the first LOD. The next step is to determine which cluster to load, and for this I am implementing a method called frustum culling. With this we can determine which cluster is inside the view frustum, and therefore we can exclude those from being rendered or being taken in the rendering pipeline. The first test run of this is quite okay. The LODs are switching, but there is a small issue where we got LOD somehow flickering. And the reason for that is there's no threshold for switching between the clusters. So for example, if we have two distances where we swap our LODs, so let's say the camera has the distance greater than 1, then we will be switching to LOD 1. And the same thing happens to LOD 2 as well. If the camera has the distance greater than 2, then LOD 2 will be loading in. But we also have to consider the other way around of switching. And this time we start at LOD 2. So if the distance of the camera is less than 2, then we switch to LOD 1, and if the camera distance is less than 1, then we switch to LOD 0. And since we are just switching LODs greater or less from a constant, we got a floating point accuracy issue where the last few digits can change, and therefore the distance could be above or below a set switching distance. Therefore, it is very sensitive on the changes on the last few digits. And after adding the threshold in, the system runs fine. The reason why I said fine is because this runs well on smaller meshes. As soon as I load it in a larger model, it takes up to 5 minutes to load and process that model. And the issue here is I do a deep copy of each primitive for each cluster, and the copying is what causes the long loading time. After all of the pre-processing is done, I only got a few FPS. This is coming from this line of code, where I rebuild the whole model each frame and submit this mesh data each frame for it to be drawn here, and this massively tanks the performance. But before we go further, there is something that I need to share with you guys. Pablo.
Albert Einstein! It's Albert Einstein! Oh my god! It's Albert Einstein! Oh my god!
Now, while it is working, I just couldn't let this be in this way. And instead of going back, I went back to the drawing board and resketched the whole architecture again from the ground up. And here is the result of the rebuild of the engine. It is now running way faster, and the pre-processing time is also down to just a minute. The pipeline itself hasn't changed, so we got our first stage with clustering, and then simplification, and then the LOD switching and transition. the overall data structure has changed, and instead of relying on GLM, I am now using my own math library, which uses AVX and SIMD for vector and matrices operations. Additionally, instead of using OpenGL as the renderer, I switched to Vulkan. This was easy to say, but in reality, it was a hassle. So before I was building the whole mesh again each frame. Now the whole mesh with the LOD data is being uploaded up front, and in each frame we only pick and choose which cluster to draw via a graph. So that's it for today's video. I hope that this video was interesting to follow, and thank you for watching and clicking on this video, and have a nice day.